Hello everyone and welcome to this lecture on smart agriculture in Japan. My name is Mitsuhiko Katahira and I'm a professor at Yamagata University. Today, I will introduce how technologies such as IoT, big data, and artificial intelligence are transforming modern agriculture in Japan. Throughout this lecture, I will also present several practical examples from my own research. For example, this image shows our AI-based system for detecting safflower flowers and buds. Our AI model can accurately identify flowers and buds directly from field images. I will come back to this example later in the lecture. Now, let me begin with a brief introduction of myself. First of all, let me introduce myself. My name is Mitsuhiko Katahira, and I'm a professor at Yamagata University in Japan. My research field is agricultural machinery engineering. My main research interests include smart agriculture, the development of seeding machines for direct rice seeding, and post-harvest technologies such as rice drying and processing. More recently, I have also been conducting research on data-driven agriculture productions using AI and big data. This slide shows my career path. As you can see, I have worked in industry, local government, and academia. I began my career in my private company where I was involved in the design and installation of refrigeration systems. After that, I worked as agricultural engineer for the Akita Prefecture government, developing agricultural machinery tailored to local farming needs. I then joined Yamagata University, where I have continued my research in agricultural machinery, smart agriculture, and data-driven farming technologies. Because of this diverse background, I believe one of my strengths is my experience across industry, government, and academia. This experience allows me to bridge fundamental research and practical agriculture applications. In recent years, digital transformation in agriculture and smart agriculture have become major topics in Japan. These technologies are being introduced to improve productivity, reduce labor requirements, and address the shortage of agricultural workers. In this lecture, I will introduce several examples of smart agriculture and explain how these technologies are being applied in Japan. This photograph shows a robotic rice transplanter manufactured by Kubota. The field shown here is the Takasaka Experimental Farm of Yamagata University. This robotic transplanter is equipped with a GNSS guidance system and automatic steering. It can maintain straight planting rows with high accuracy and automatically turn at the headland, reducing the operator's workload. Now, let's consider why smart agriculture has become so important in Japan. Japanese agriculture is currently facing several major challenges. First, Declining rice consumption and falling rice prices have reduced agriculture income. Second, fewer young people are entering agriculture while the farming population continues to age. Please look at this figure. It shows the number of new farmers in Japan by age group. As you can see, a large population of new farmers are over 50 years. This means that Japan has relatively few young people entering agriculture. Another major challenge is the transfer of agricultural knowledge and skills. Becoming a skilled farmer requires many years of experience. One useful framework for understanding this process is the Draper's model of skill acquisition. The model describes how people develop professional skills through experience and consists of 5 stages, from novice to expert. In agriculture, reaching the expert level often requires around 10 years of field experience. One of the goals of AI is to capture the knowledge and decision-making process of experienced farmers and make them available to less experienced farmers through data-driven decision support. This is why smart agriculture and AI are expected to play an increasingly important role in the future of Japanese agriculture. Now that we have discussed IoT, big data, and AI, let us bring these technologies together. What is smart agriculture? Smart agriculture is application of advanced technologies such as robots, AI, IoT, and GNSS to agricultural production. The goal is solve practical problems faced by farmers and make agriculture more efficient, productive, and sustainable. The concept of smart agriculture can be summarized by 3 main components: automation, the use of big data, and information sharing platform. Together, these technologies provide several important benefits. First, robot helps reduce labor requirements through automation. Second, AI and big data enable more accurate predictions and better decision making. Third, digital platforms create new value chains by connecting farmers, consumers, and other stakeholders. In the next section, I will explain 3 key technologies that make smart agriculture possible: IoT, big data, and artificial intelligence. These 3 key technologies. The first technology is the Internet of Things, or IoT. IoT refers to technology in which physical objects are equipped with sensors and connected to a network, enable data to be collected and utilized in real time. In agriculture, IoT has been widely applied to monitor environmental conditions, crop growth, and livestock production. Our research is an example of IoT technology for chicken farming. This figure illustrates our RFID-based automatic body weight measuring system for chickens. Each chicken wears a leg band RFID tag for individual identification. When a chicken steps on the weighting platform, Its RFID, tag ID, and body weight were recorded simultaneously. In addition, RGB cameras monitor drinking and growth behavior, while a thermal sensor measures body surface temperature. These multimodal data are integrated into a single database for each individual chicken. The following video demonstrates real-time chicken detection and body weight measuring using AI. As you can see, the system automatically identifies each chicken and measures its body weight in real time without manual handling. This system continuously collects data from multiple sensors, making it a practical example of IoT in precision livestock farming. Second, the second key technology is big data analytics. Big data refers to collection and analysis of large volumes of data, diverse data that can be processed efficiently using modern computing technologies. In agriculture, recent advances in UAVs, sensors, and AI have made it possible to analyze extremely large image datasets within a short time. Traditionally, crop growth was evaluated by selecting several sampling points within a field. Example 1, 2, 3. These samples provide useful statistical information, but they represented only a small portion of the entire field. Today, AI can detect every soybean plant and every weed directly from UAV image. Instead of estimating field conditions from a limited number of samples, we can analyze the entire field. This enables more comprehensive and objective observations while reducing uncertainty associated with manual sampling. More accurate information leads to more reliable predictions and better decision making. For this reason, big data analytics is now being applied not only in agriculture but also in transportation, healthcare, manufacturing, and many other areas of society. However, collecting a large amount of data alone is not sufficient. We also need methods to analyze the data correctly and avoid misleading intuitive judgments. The following example illustrates why human intuition can something be misleading. Please take a moment to think about this question. A bat and ball cost a total of 110 yen. The bat costs 100 yen more than the ball. How much does the ball cost? The correct answer is 5 yen. If the ball costs 5 yen, then the bat costs 105 yen, giving a total of 110 yen. Interestingly, more people answer 10 yen. When I asked this question in my class, The most common answer is also 10 yen. This does not mean people are careless. Rather, it shows that we naturally rely on fast, intuitive thinking before performing a careful calculation. Even highly educated people often answer 10 yen because the human brain naturally relies on intuitive thinking before analytical reasoning. Big data analytics helps reduce this type intuitive bias by enabling decision based on objective data rather than intuition alone. To analyze enormous amount of data, we need artificial intelligence. Recent advances in deep learning have made it possible to extract meaningful information from complex data such as images, videos, and sensor signals. This is exactly where artificial intelligence becomes important. Let's now look at how AI and deep learning make this possible. Let's first look at conventional machine learning. In conventional machine learning, humans manually designed image features such as edges, corners, and textures. These handcrafted features were then classified using algorithms such as support vector machines. The recognition performance depended heavily on how well humans designed these features. However, this approach had several limitations. Feature extraction required expert knowledge. Spatial relationships among image features were not fully utilized. Recognition performance decreased when object appearance changed. These limitations motivated the development of deep learning. Deep learning is inspired by the structure of the human brain. It uses artificial neural network composed of many interconnected layers that automatically learn useful image features directly from data. Unlike conventional machine learning, feature extraction and classification are performed automatically within a single neural network. Artificial intelligence has existed since the 1950s. However, computers at that time were not powerful enough to train large neural networks. Even during the second AI boom in the 1980s, neural networks typically consisted of only a few layers. The major background comes with modern GPUs, which enable massive parallel computation. Today, deep neural networks may contain dozens or even hundreds of layers, dramatically improving imaging recognition performances. Around 2012, Google demonstrated that a deep neural network trained on millions of images could automatically recognize cats with explicitly being programmed to do so. Accuracy. Recognition performance can be further improved through optimized network architectures, activation functions, and data augmentation. Today, deep learning is widely used in agriculture, autonomous driving, medical diagnosis, robotics, and many other fields. The soybean and chicken example showed earlier a practical application of exactly this technology. What can one say about the future agriculture? We are now in the age of new society. It is the so-called Society 5.0. Agriculture must also adapt to Society 5.0. I think that the key concept is smart agriculture, as I have explained for earlier slides. In the past, agriculture has been based on cooperation between nature and humans, traditionally. Today, machines have become a third partner in agriculture. In the future, agriculture will integrate nature, humans, and machines into a digital twin environment where they support one another. This integration contributes to sustainable agriculture and the achievement of the SDGs. The future should not discard the past. Instead, it should build upon the wisdom accumulated over generations. The future of agriculture lies in integrating traditional farming wisdom with data-driven technologies, rather than relying on either one alone. Let me now show you some practical examples of how this concept is being implemented in Japan. Next, I would like to introduce some examples of agricultural robots developed in Japan. These robots have been designed to solve labor shortage and reduce the physical workload of farmers. This robot was developed at Utsunomiya University to harvest strawberries automatically. Using image captured by CCD camera and AI-based vision system, they detect ripe strawberries. The robotic end effector gently grabs the stem and places each strawberry into a dedicated container. Because the fruit itself is not touched, damage is minimized, and the storage life of the strawberries can be extended. These high-quality strawberries can be sold for approximately 1,000 Japanese yen or about $7 per fruit. Another example is our watermelon transport robot, which is being developed jointly by Yamagata University and Ishii Manufacturing. Watermelons are heavy, and transporting them from the field to a truck requires considering physical effort. This robot is designed to carry harvested watermelons automatically, reducing the workload of farmers. Please watch these short videos demonstrating how the robot operates in the field. These examples demonstrate how AI and robotics can work together to solve practical problems in agriculture. Next, I would like to introduce examples of autonomous agriculture machinery used in Japan. This slide shows robotic rice transplanter and robotic tractor for direct rice seeding. These machines are equipped with RTK GNSS positioning, automatic steering, and multiple safety systems. Compared with conventional DGPS, RTK-GNSS provides centimeter-level positioning accuracy, enabling highly precise field operations. The Main object of these robotic machines are to improve operational efficiency, reduce labor requirement, and achieve more accurate field operations. This video shows direct seeding of rice using robotic tractor. The tractor performs paddling and direct seeding simultaneously. When it reaches the headland, it automatically lifts the rotary harrow, make a turn, and accurately aligns itself with the next pass before continuing the operation. The positioning error is only a few centimeters, demonstrating the high precision of RTK GNSS guidance. This level of accuracy was almost impossible to achieve with conventional manual operation. This level of positioning accuracy is essential for precision agriculture and serves as a foundation for autonomous field operations. This figure shows the main components of robotic tractor system. An RTK GNS antenna mounted on the tractor roof receives satellite positioning signals. The receiver and display monitor continuously shows the tractor's current position, travel direction, and guidance path. A steering controller and electric steering monitor automatically controls the steering wheel, allowing the tractor to follow the planted route with centimeter-level accuracy. The operator can monitor the tractor's position and operating status in real time on this display. One of the major advantages of this system is that it enables precise field operations even under challenging conditions, such as when conventional marker tractors are difficult to create, difficult to see, including after sunset. This improves operational efficiency and positioning accuracy while reducing the operator's workload. Reliable positioning provided by RTK GNSS enables precise field operations regardless of field conditions or time of day, forming the foundation for autonomous agricultural machinery. Next, I would like to introduce an autonomous weeding robot used in paddy fields. These robots follow a predefined route using automatic navigation and move throughout the paddy field without human operation. The robot has two rotating paddle wheels that steer the surface soil and water. This disturbs the germination and growth of weeds, reducing weed competition without using herbicides. The video on the left shows an early prototype, while the video on the right shows the latest models. The name Aigamo comes from the Aigamo duck, which has traditionally been used for biological weed control in Japanese organic rice farming. This slide shows robotic combine harvesters. Upside videos shows head feeding type combine harvester. Underside shows ordinary type combine harvester equipped reel type for header. The head feeding type is special to Japan. This robotic combine harvester can harvest rice while measuring the rice yield and water contents. This technology can decrease the variance of rice yield by combining drone sensing and variable fertilization. Now let's watch a short video introducing the structure of combine harvester. Please pay attention to its main components and how the machine operates.
Good morning. Today I will show you combine harvesting and explain the structure of combine. I'm now cleaning a combine, so you can see the threshing drum, feed chain, and so on. I will explain the flow of harvesting works unit by unit. This is a reaping unit. This is called a header, which gathers rice hills. Rice hills gather here, and this device is called divider. Rice hills are inserted into this device and transported upward. Cutters are located underneath. They are clipper blades. Here, rice hills entering like this, and the blades reciprocate. The lower blades are fixed, and the upper blades reciprocate left and right, and the rice is cut. Transported rice is now moving in this direction. The device holds the rice hills and lifts them. Then feed chain holds the foot of rice hills, and the rice hills lie down with panicles on this side. The panicles are on this side. The panicles move like this, and rice hills lying down this way, and the feed chain holds the foot side. This part on the upper side meshes with feed chain, so they hold tight the foot of the rice hill. Then the rice moves towards threshing drum. Threshing drum rotates at high speed. Panicles move on, passing underneath the threshing drum. Panicles pass underneath, while threshing drum rotates at high speed and thresh paddy from panicles. Only panicles enter between receiving net and threshing drum, and the paddy is threshed. Threshed paddy falls through the net. Long straws are caught here. Paddy and straw scraps pass through receiving net and fall on the sieve called grain pan. The paddy and the straw scraps fall onto this part. This sieve oscillates back and forth to separate paddy and straw scraps. Separated paddy falls from here onto the sieve called grain sieve, which separates sound paddy from others. Sound paddy falls down and goes to grain tank located at the back. Paddy is transported by a huge screw called auger to the grain tank. Straw scraps and immature grains are conveyed to shaft sieve located behind the grain pan. Straw scraps enter shaft sieve and are discharged from the rear end. After threshing, feed chain continues to carry straw to the rear end. I am on the other side of the combine. Grain tank, which keeps paddy, is located on the other side of the threshing drum. Separated sound paddy is conveyed by this transverse conveyance screw called the first auger and passes through this pipe to the grain tank. This is the grain tank which keeps threshed paddy. The capacity is about 1 cubic meter or 1,000 liter. The capacity depends on the combine model, 1,000 liter or 1,500 liter. The capacity of this tank is 1,000 liter, and paddy is kept here. In Japan, about 3,000 liter of paddy is harvested from a paddy field of 0.3 hectare. Three times the full capacity of this tank. When the tank is full, but is unloaded. The vertical auger conveys body to the swing arm. This is the swing arm. Body passes the swing arm and is unloaded to a truck. This is how combine works. This is a fan of the winnower. The airflow from here blows off light matters such as straw scraps which pass the sieve out of the rear end. This is the outlet. Waste straw is shredded into pieces about 20 centimeters long and spread over the paddy field. The length of shredded straw is about 20 centimeters. Paddy fields should be dried well prior to harvesting. Press the soil with your finger, and if the finger mark remains, the soil is hard enough. It would be better if the soil is drier. Still, we can work sufficiently even in this condition. But the surface of a headland is scraped off, so we need to harden the soil a little bit more. Otherwise, we can damage paddy field. It is important to harden the soil. Please take a look at this. These are fallen grains. When Japanese combine harvester is used, the harvest loss is around 5%. The grains fail during reaping and threshing, but the summer immature grains blown off by winnower. This area was harvested, but it isn't covered with waste straw yet, so we can see the harvest loss. The rice is cut 10 centimeters from the ground.
Next, I would like to introduce how UAV imagery is collected and processed for smart agriculture. Although this UAV is small and lightweight, it can fly for relatively long time and capture high-resolution 4K images. It also follows an automatic flight path created using mission planning software, allowing images of the entire field to be collected efficiently. The captured images are then processed using photogrammetry software to generate also mosaic images and three-dimensional models. These georeferenced datasets can be analyzed using GIS software, such as QGIS, to visualize field conditions and support agricultural decision-making. This workflow provides a foundation for many data-driven applications in smart agriculture. Next, let's watch a short videos demonstrating how an agriculture UAV operates in the field. Please pay attention to its structure and spraying operation.
In Shonai region, liquid agrochemicals are applied to the paddy field, mostly by radio-controlled helicopter. Radio-controlled helicopter sprays fungicides for rice blast and seed blight, and insecticides to control stink bugs. Farmers rather pay an agriculture cooperative or a private company to spray agrochemicals for them, because helicopter is expensive. The helicopter is equipped with a petrol engine, and its maximum flight time is approximately 100 minutes. It flies 3 to 4 meters above the ground at a speed of 10 to 20 km per hour and sprays 8 to 10 liters per hectare with a spray width of 7.5 meters. It takes about 6 minutes to spray 1 hectare. It can carry up to 32 liters of liquid agrochemical and spray 3 to 4 hectares per flight. The price of a helicopter is over 10 million yen, while the helicopter operator charges 2,000 to 3,000 yen per 0.1 hectare. The farm area sprayed by drone is increasing rapidly because a drone is cheaper than a helicopter. Some drone sprayer can be purchased at 600,000 yen or less, and the price is expected to be cheaper and cheaper. Individual farmers or agricultural corporations purchase a drone so that they can spray whenever it is convenient, unlike the scheduled spraying by helicopter operator. Apart from spraying agrochemicals, the drone can be used for sowing and applying fertilizers. Neither radio-controlled helicopter nor drone is allowed to spray when the wind speed exceeds 3 meters per second. The drone is equipped with 6 rotors and 2 rechargeable batteries, and flies 3 to 4 meters above the ground at a speed of 10 to 20 meters per hour. It can carry up to 5 liters of liquid agrochemical and spray 0.8 to 1 liter per minute, with a spray width of 4 meters. Its maximum flight time is approximately 10 minutes, and it can spray 1 hectare per flight.
Next, I would like to introduce the visualization of rice growth using UAV technology. The main objective of this system are, first, to visualize rice growth conditions across the entire field. Second, to maximize the yield while maintaining grain quality. Third, to reduce labor by evaluating crop growth and applying fertilizer only where it is needed. First, rice growth is measured using a UAV equipped with a near-infrared or near-NIR camera. This one. The UAV captures images of the entire field in just a few minutes. Using the red and near-infrared bands, the system calculates vegetation indices such as NDVI to estimate crop growth and nitrogen status. Next, the growth information is converted into a leaf color map. This map visualizes spatial variations in crop growth across the field. Based on this information, a visual rate fertilization map is automatically generated. Finally, farmers apply fertilizer according to the prescription map using visual rate application equipment such as UAVs or GNSS guided fertilizer spreaders. As a result, fertilizer is applied only where it is needed, improving fertilizer efficiency while maintaining yield and grain quality. This is another example of data-driven agriculture, where sensing, data analysis, and precision field operations are integrated into a single production system. Next, let me briefly explain remote sensing and NDVI, or Normalized Difference Vegetation Index. Healthy rice plants absorb a large amount of red light for photosynthesis while reflecting a large amount of near-infrared, or NIR light. As rice grows more vigorously, the difference between red and NIR reflectance becomes larger. The NDVI is based on this difference and is widely used as an indicator of crop growth and vegetation vigor. The graph on the left illustrated the spectral reflectance characteristics of rice, and the equation above shows how the NDVI is calculated from the red and NIR reflectance values. First, the UAV captures multispectral images containing the red, green, blue, and near-infrared band. These images are processed to generate also mosaic images for each spectral band. Finally, the red and NIR images are substituted into the NDVI equation to generate an NDVI map. The resulting NDVI image visualizes spatial variations in crop growth and provides valuable information for precision crop management. These graphs show the relationship between NDVI and nitrogen uptake for the three major Japanese rice varieties. As you can see, the relationship is consistently positive. The other words, higher NDVI value generally indicate greater nitrogen uptake and more vigorous crop growth. This relationship provides a sufficient basis for using UAV remote sensing to evaluate rice growth and support fertilizer management. I will explain the next stage of rice growth monitoring. Remote sensing and AI are two technologies that can play an integral role in assisting farmers to increase productivity while reducing labor requirements. Remote sensing devices can collect widely various field data in real time or in near real time. AI can analyze these data quickly. The system can transmit results back to farmers to inform better decisions that can enable better productivity quickly. Three key components are needed to develop a next stage crop monitoring system: a method to collect data using remote sensing, a method to analyze the collected AI, and finally, method to communicate the information obtained to the end user, equal farmer. They are visual growth maps in GIS that are easy to understand. This slide shows an image from Livestock Industry Exhibition in Europe, 2018. The livestock sector is being robotized for many tasks necessary for caring for animals. This system measures chicken weight and uses group management. These robots are cleaning livestock facilities. This image shows a feeding robot for cows. This image shows a milking robot. It is being introduced in Japan as well. IoT and robot technologies are also being introduced for use with field machinery. These robots are used for mowing on slopes. These robots are soil sampling robots that record sampling location by a GNSS system. After the obtained sampling data are analyzed at laboratory, those data are used along with geographic information. European countries are introducing links with robots and data aggressively. Similarly, in Japan, the Ministry of Agriculture, Forestry and Fisheries is introducing linkage of robots and data. These are stores and transport devices for UAV. This device detects crops by object detection AI. It also detects weeds while avoiding crops. These had already been commercialized as of 2019. Next, I would like to introduce one of our research projects at Yamagata University, the development of safflower harvesting system. Safflower has been cultivated in Yamagata Prefecture for hundreds of years and is one of the region's traditional specialty crops. In Japan, safflower petals have traditionally been used to produce natural dyes, cosmetics, and lipsticks. However, harvesting safflower is still carried out manually during the hot summer seasons. In addition, safflower plants have many sharp thorns, making harvesting physically demanding and time-consuming. As a result, the number of safflower growers have been decreasing in recent years. To address this problem, we have been developing a more efficient harvesting system for safflower. This video shows our field experiment using a clipper-type T harvester to investigate whether it can be adapted for safflower harvesting. This is an example of applying existing agricultural machinery to solve a labor shortage in specialty crop production. This slide shows the basic concept of our robotic safflower harvesting system. The system consists of three main components: First, a mobile platform that moves through the field. Second, an image capture system equipped with a camera. Third, a parallel link robot arm for harvesting the petals. The camera captures images of safflower plants, and an AI-based object detection model identifies the flower petals automatically. The AI calculates the X and Y coordinates of each detected flower and sends the information to the controller computer. Using these coordinates, the parallel link robotic arm moves precisely to the target flower for harvesting. This system demonstrates how AI-based precision and robotic manipulation can be integrated into an autonomous harvesting system. In other words, AI functions as the eyes of the robot, while the robotic arm functions as its heart. Together, they enable autonomous harvesting. Next slide, system components of safflower robot harvester with AI. I used YOLO for object detection AI. The parallel link robot arm was controlled by ROS called ROS. I used Arduino Uno to control the servo motors. The AI system was able to detect safflower petals with 80 to 90% accuracy by running 10,000 times using more than 400 images. The detection accuracies for image and video are almost identical. Safflower petal detection by AI is affected by differences of number of learning. I would like to introduce our current research on rice growth monitoring system using a UGV or unmanned ground vehicle. The goal of this research is not simply to collect data. Rather, we aim to sufficiently analyze the intuition and experience that skilled farmers have developed over many years. The UGV collects various types of field data, including crop growth and environmental information, which are integrated with UAV and cloud-based data. These data are used to maintain productivity, improve farm profitability, and support data-driven decision-making. Ultimately, we hope this technology will help transfer agriculture knowledge to next generation by converting farmers' experience into digital data that can be shared, analyzed, and reused. I will introduce about our field robots. The field robot is 140 centimeter long with 120 centimeter width and 145 centimeter height. Its approximate weight is 180 kilograms. Two 12-volt batteries supply power to 4 brushless electric motors that rotate each of the 4 wheels. 1, 2, 3, 4. The 65 centimeter diameter wheels are of a similar type of those used on rice transplanting machines. The robot operation is by remote control, as an GNSS antenna on the top. With two Sony action cams for image and video capture. This robot equips the sensor box to measure field conditions. Inside the sensor box are sensors for temperature, humidity, sunshine, etc., which are connected to the control software. Data are recorded and stored on a micro SD card. The robot used to capture images from entire field. This table presents details about the data collected for each field. The captured image was then passed to the deep learning model for analysis. This video shows samples of in-field detection of rice tillers. We calculated rice tillers into 3 classes. This video shows classified number of rice tillers below 11 to 20 and above 20 by object detection AI. Next, we flow a workflow for visualization of AI detection shown here. The AI image and RTK GPS data are merged. These merged data are imported into GIS. Filtering is done to remove duplicates and overlap images. Tiller per square meter are calculated and shown. Then, comparisons are made with ground truth data. To compare the AI estimation and ground truth data, we must first consider the characteristics of the two sets of data. The AI estimation is derived from images captured in the entire field, where many plants are analyzed. The data are then classified to 3 categories. The ground truth data are taken from a limited number of places in the field. A small number of plants measured to get the exact number of tiller per plant. Therefore, it is necessary to bring these two datasets to a common metric for comparison. In this case, we use percentage. We calculate the percentages of each class detected in the field for the AI estimation. For the ground truth data, we first assign each plant in the same classes or categories as the AI. Then we calculate the percentages. This tiller per square meter range from below 50 to 158 depending on the location in the field. As might apparent from the gross map, areas around the center row of the field appeared to have more tiller per square meter, 150. Whereas the lowest tillers per square meter, less than 50, were primarily along the bottom rows. I'm sure you will find out soon which one is correct. GIS enables us to visualize agriculture data spatially. Spatial agriculture data provide opportunities for precision management. If we were to consider results from AI analysis alone, then we would only be able to say how many plants were detected in each class. However, if we added spatial data to the AI analysis, then we can say what was detected and where. Our field robot was developed to use for crop growth monitoring, but it can be adapted for other applications such as the following. Using low-mounted cameras to collect image from under the crop canopy of disease detection. Attachment to detect and eliminate weeds as shown here, with robot arm to press weeds into the soil or using chains to remove weeds during data collection. Additionally, because of design, the robot is useful for many other row crops. Next, I would like to introduce an example of smart technology developed for watermelon cultivation. In this study, aerial images of watermelon field were captured using a UAV. Based on these images, we automatically estimated the locations and the number of watermelon in the field. The positions of the watermelons were detected using an AI-based object detection model, together with our prototype object tracking software. The detected information was automatically recorded in Google Spreadsheet for further analysis and management. Finally, the detected watermelon locations were mapped using GIS software, allowing farmers to visualize the spatial distributions of watermelons across the field. This is another practical example of data-driven agriculture, where UAVs, AI, cloud service, and GIS technologies are integrated to support agricultural productions. This is an example of a smart agriculture information system developed for watermelon production. The system distributes daily forecasts of shipping quantities and expected harvest date to farmers through the line messaging application. First, the air temperature data are collected by weather stations installed in the field and transmitted to a data server. The web server then calculates the accumulated temperature from the pollution date to the current day. The calculated accumulated temperature is periodically retrieved using a program developed with Google Script and recorded in a Google spreadsheet. Using the accumulated temperature together with historical daily average temperatures for the region, the system estimates the expected harvest date. Every morning, farmers automatically receive information such as the predicted harvest date and the estimated number of harvestable watermelons through the LINE smartphone application. This system is a practical example of data-driven decision support in smart agriculture. What does the future of smart agriculture look like? This video shows a robotic tractor sowing wheat in the field. I believe smart agriculture will bring several important benefits. First, it can reduce labor requirements and production costs. Second, data collected from variable sensing devices can visualize field conditions and provide valuable insight for farmers. Third, digital technology can help transfer agriculture knowledge and skills to less experienced farmers. Finally, smart agriculture can improve safety by reducing accidents and minimizing hazardous operations. Ultimately, the future of smart agriculture lies in building data-driven agriculture production systems that create value from digital information. I believe the future of agriculture is not simply about introducing more technology. It is about creating value from data while combining advanced technologies with the experience and wisdom of farmers. Conclusions. Yamagata University is actively applying smart agriculture technologies to wide variety of agriculture production systems. Ultimately, the future of smart agriculture lies in building data-driven agriculture production systems that create value from digital information. By integrating digital technologies with the knowledge and experience of farmers, we can build agriculture systems that are more productivity, sustainable, and resilient for future generations. Thank you very much for watching this lecture. I hope it has given you a better understanding of smart agriculture in Japan. Thank you very much.